Okay, so now we can finally start doing the questions of heat and work along with first law of thermodynamics. So these are combined questions, and these types of questions where a piston and cylinder with stops is given, they are quite common. And while there isn't like a procedure to them, there is a general method to them that you have to follow. I would advise you not to question this general method too much because it does seem a bit skeptical at first, but rest assured it will always give you the right answer. With that being said, I think there's around 10-15 problems in this tutorial, and this is quite an important tutorial. And yeah, let's begin. The piston cylinder in the figure given below contains zero point 0.1 kilogram of water. Let's just draw this. Water 0.1 kilogram at state 1 with T1 of 500 degrees Celsius and P1 of 1000 kilopascals. The piston has to stop at half of the original volume. Is the original volume given? No. Okay. So V1 is some V. And then this piston must come over here so that volume becomes half. After that, the water cools to a room temperature of 25 degrees Celsius. So here it is given in the question that the piston has to stop at half the original volume and then the water will cool down. So here the piston will stop at half the original volume at state 2 at some T2 at some P2 and at some V2 equals to V by 2, and then it will cool down. To 25 degrees Celsius, and this is state 3. So now what is going on here? An important thing to note is 1 to 2 has pressure as constant and 2 to 3 has volume as constant. 2 to 3 is very obvious, right? That volume is constant because the piston has come down first and then it has cooled down to the room temperature. So we can understand that 2 to 3 somewhere is making sense that volume is constant. But why is 1 to 2 a constant pressure process? That is what we have to do. So to explain this, you can think of it like atmospheric pressure is constant and that will force the piston down. The energy, some form of energy loss will be occurring here, whether it be heat or something, and then that will result in the piston moving down at constant pressure because the atmospheric pressure that is forcing it down is constant. Again, the thing that is going on here is that piston will lose some energy. That will cause, the container will lose some energy. That is, the water inside the container will lose some energy. Then the piston will be forced down by the atmospheric pressure. Since the atmospheric pressure is constant, we can say that 1 to 2 is happening against a constant pressure. Right? So we're going to do a lot of these types of questions where which will happen in 3 stages. That is, first it will expand, then the pressure will increase, or first it will expand ka ulta, what do you call it, compress. First the piston will compress and then the temperature will decrease like it's happening here. So we're going to look at all of these cases, right? So now that we have all of the information sorry, now that we know we don't have all the information yet. Now that we know what is going on in the question and what the situation looks like at 1, 2, and 3, what I always find helpful to do is to find all of the states at 1 to 3. That is all of the information at 1 to 3. That is like U or S, which will come later on, and volume, specific volume, VF, state, etc. etc. Right? So let us begin by doing that at 1. We have been given water at 500 degrees Celsius and 1000 kilopascals. Right. So now step 1 is to determine the state of water at 1 using the thermotables, right? Let us quickly draw our TV diagram over here. This is the 1000 kilopascal line. At 1000 kilopascal, what is our saturation temperature? Let us look at thermotables. We want saturated water pressure entry, right? Because we are using 1000 kilopascals to find the saturation temperature. Right, so if we keep seeing, then at 1000 kilopascals, our saturation temperature comes out to be this much. So this is 179.91 degrees Celsius. However, our given pressure is 500 degrees Celsius, which means it is somewhere over here. As the intersection point lies here, that means it is superheated. Is superheated. That means we can find the specific volume, from the superheated table. Right. Let us go to the superheated tables next. Okay, 10, 50, keep going, 400, okay, 1000 kilopascals. If you see in the bracket of the heading in the superheated table, the T sat at that given P at given pressure is given, right? As we saw, 179.91 is the saturation temperature at 1000 kilopascals. Just extra information. Always good to know. In case you're not able to use the regular tables, you can always refer to the superheated tables. So 1000 kilopascals and 500 degrees Celsius has a specific volume of 0.35411. V1 equals to 0.35411. As we know the mass, remember mass is 0.1 kilogram given in the question, and specific volume is volume by mass. We can say small v into small m, or just m, is equal to capital V, which means the volume of container at the initial state is 0.35411 into 0.1 equals to 0.035411 meter cube. Just meter cube, because now we have multiplied mass, right? Then U at 1 from same table. So the value of U is given in the second column. It is this 3124.34 kilojoule per kilogram. The value of U and S and such is given in kilojoule per kilogram. So you have to be careful while using it in numerical to convert it to joules, right? So U1 equals to 0.35411 kilojoule per kilogram. Right. So now we have acquired all the info we possibly can at 1. Now we will do the same exact thing for state 2. We have water at some temperature T2. Remember, the water is losing some energy, right? So we don't know what exactly that energy loss is in, but as we will see, the temperature from 1 to 2 will decrease. That is why the piston is coming down. That is why the atmospheric pressure is compressing it at a constant pressure, and that is why 1 to 2 is also constant pressure process. Anyways, water at some T2 and P equals to 1000 kilopascals. Right? Also, V2 equals to capital V1 by 2, or you could have just done it by specific volume terms as well, because mass on both sides will cancel out, which implies V2 equals to 0.177055 meter cube per kg. So now what is the state at 2? Right, so step 1 is to state at 2. Let us draw a diagram. This time, since we have been given the pressure, let us draw the PV diagram. Remember, it is inverted. And let us try and find the VF and VG values. Right. So going back to our tables here and looking at saturated water pressure entry, again at 1000 kilopascals, we will get VF to be this value and VG to be this value. So VF is this 0.001127 and VG is this. Our given value of V2 lies somewhere in the middle. That is, it lies on this line, which means saturated mixture. Now, since it is a saturated mixture, we cannot directly find the value of U and all, right? First, we will have to determine the quality factor. Value of V we were able to directly find because it was given to us that the value of V is halved from the initial state. But you can't say the same for U, right? So now, step 2 was to find value of V, which we have already been given as half of the initial, that is this. And step 3, U at 2. So how will we find U? If you remember, I taught you this formula. V equals to Vf plus X Vfg. Right. The same formula can be applied to U also. U equals to Uf plus X into Ufg. So in this equation, we have to find this and we have to find this. These two values are given in the table, right? We can always get it from the table at 1000 kilopascals, right? Because that is the pressure at 2. So we have to find U and X. So obviously there is only one equation and two variable. We can't solve it, right? So if you notice carefully, in this equation, we know everything except X. Right? In this equation, we know the value of V, that is this. We know the value of Vf, that is this. Vfg can be found in the table, it is given. In fact, let us see the value of Vfg right now. If you see, this is the Vfg column and it is this 0.19332. So we know this, and we know this. Thus, the value of x can be very easily calculated. So plugging all of this information into this, we will get x equals to 0.912. That is, the quality of the mixture is 91.2%, or it is mostly in vapor phase, right? Because remember, quality can be intuitively thought of as the mass of vapor upon total mass. That is, mass percent of vapor is the quality. So now we have the value of x. Coming back to our original equation that we had to solve, value of u we can get from the table, uf we can get from the table, ufg we can get from the table, value of x we have found from the above equations. So we will be able to find the value of u at this state. Now some people might have a doubt, why are we using the uf and ufg values at the saturation temperature, sorry, at the given pressure that is of 1000 kilopascals. First, it is because pressure is constant from 1 to 2 at 1000 kilopascals, and state 2 exists at 1000 kilopascals, right? And that, if you remember, that is how we calculated the state. If you are confused still, go back and watch the finding the state video, right? So we will find the values of uf and ufg at 1000 kilopascals. It is given to be 761.67 and 1821.97. And 1821.9 something. Okay, so if you solve this, the value of internal energy at the second state will come out to be 2419.66 kilojoule per kilogram. An interesting thing that you will notice is that at this state, the temperature will be the same as the saturation temperature, because it is a saturated mixture. And if we see at 1000 kilopascals, a temperature of saturation is 179 degrees Celsius. That means from the initial state of 250 degrees Celsius, of 500 degrees, 500 degrees Celsius, yes, from initial state of 500 degrees Celsius, it has lost some heat, loss of heat, which is why the energy of the water has been lost, which is why the piston has come down and it has gone to 179 degrees Celsius. However, since it is given in the question that the piston will come to 25 degrees Celsius, some further loss of heat must be occurring from 2 to 3 as well. However, we will solve all that later. Right now our primary focus is to find all of the data at the given states, right? So now at state 2 we have the specific volume, specific internal energy, volume and temperature. Let us try to do the same at state 3. At state 3, what do we have? We have a temperature of 25 degrees Celsius and the specific volume remains the same because the volume remains the same, right? Because remember, once the volume has been halved from 1 to 2, the piston can't move further down because of the stops. So the value of this was 0.177, right? So again, our step 1 is to determine state at 3. Since we are given temperature, let us draw the TV graph. Vf and Vg. We're using Vf and Vg because we know the temperature and the specific volume. At 25 degrees Celsius, our Vf is given by this, and our Vg is given by, oops, sorry, and our Vg is given by this. So let us write those down. Vf equals to 0.001003, Vg equals to 43.3593. That means again our given volume is somewhere over here. That is, it lies on the saturated mixture line. So at 3 also it is a saturated mixture. However, a very interesting thing that you will notice is that the quality factor this time will be much different. Let us see why is that. V equals to Vf plus X into Vfg. Both Vf and Vfg have changed because now we are at 25 degrees Celsius. And Psat, again this pressure will be the saturation pressure because we are a saturated mixture. Before we were at 179 degrees Celsius and 1000 kilopascals. So obviously as our state has changed, our values of Vf and Vfg will also change. So I want you to put the values of Vf and Vfg into this. After calculating, you will get X to be 0.004. That is 0.4% is the new quality. Or now mixture is mostly liquid. It has cooled down from the gas phase and come down to be liquid. Right. Again, step 2 was to find V at 3, which is already given as V2 and V3 because they are the same. 0.177055. U at 3 is again found using the formula. U3 equals to UF plus X3 UFG. Again, if you substitute the values from the tables at 25 degrees Celsius, because remember the whole thing at state 3 is happening at 25 degrees Celsius, you will get U to be 114.1 kilojoule per kilogram. So what have we achieved so far? We have achieved a complete knowledge of what the process physically looks like from this diagram, and a complete knowledge of all of the variables representing the process at each significant intermediate state, that is specific volume, pressure, temperature and internal energy. Since this 1 to 2 is a constant pressure process, it comes to be 1000 kilopascals. V3 is still V by 2, which we have found below. T3 is 25 degrees Celsius and P3 is the saturation pressure at that temperature, because as we found out, the mixture at 3 is still a saturated mixture. So P3 is 3.169 kilopascals. Right. Now let us move on to what the question is actually asking us to do. Keep in mind that the process that I have done just now, you must do regardless of what the question asks you. Because if you do even this much, right, and you don't actually answer anything the question's asking you, the teacher will know that you have clarity on what to do. You just didn't get the time to do it. So it's very important to do what I have done just now. And yeah. Okay, so sketch the possible water states in a PV diagram. I think we should do this part in the end. Okay, part B is find the final pressure and the volume. So final pressure has been found by us as the saturation pressure, because at 25 degrees Celsius it is a saturated mixture. And the final volume will be the same as that at state 2, which was yeah, this is the specific volume. If you multiply it by 0.1, you will get that. So part B has been done. Find the heat transfer and work in the process. Okay, so This is where we have to use the first law of thermodynamics. Delta Q equals to delta U plus W. In this equation, we do not know Q and we do not know W. Fortunately for us, W is quite easy to find. W from 1 to 3 is W from 1 to 2 plus W from 2 to 3, right? W from 1 to 2 was a constant pressure process, so P delta V. W from 2 to 3 was a constant volume process. If you see carefully, the volume here is not changing, right? Because the piston is still at rest on both the stops in both the states, plus 0. So W is equals to P delta V, which came out to be the pressure was held constant at 1000 kilopascal into capital V by 2. Is it capital V by 2? Delta V. V by 2 minus V. So work will come out to be negative into 10 to the power 3. Because remember, 1000 kilopascal has to be converted to Pascal. Upon solving this, your work will come out to be negative 17.75 joule. So, now you know work delta U. Delta U equals to U3 minus U1. Why are we doing this? Why are we not doing U from 1 to 2 plus U from 2 to 3? If you remember very carefully, internal energy is a state function. So if you do this or you do this, it is the exact same thing. So a conclusion that can be drawn is that you did not need to actually do this process at state 2. However, if you are just starting out, I would highly recommend that you always do this process. In the last 2-3 questions, I will begin skipping this, but for now, we have found it, even though we are not using it. So delta U comes out to be U3 minus U1. U3 is 0.177 and sorry, U3 is not this. U3 is this 114.1 minus 0.35411. Something is up here. Just give me a second. I think we have read the value wrong from the table. As we were referring to the superheated table at 1000 kilopascals and 500 degrees Celsius, let's just do that again. Thousand kilopascals and temperature in degrees Celsius at 500. Yeah, we have put the value of V, not U. Sorry. So U is 3124.34. That makes a lot more sense. Again, using common sense, you can mostly tell when you have read the value wrong. What was it? 3124 point something, right? 3124.34. 0.24. I don't know. Come on. So 114.1 or close to this value you can also get 114.2 or something. Minus 3124.24 or 34 or something like that, right? And I think work also we've made a bit of mistake. It will come out to be is it Is the meter cube given? Is it meter cube? The volume that we found. No, the work that we found was correct. Sorry. And this will come out in kilojoule, right? You will have to convert it to joule. This is kilojoule per kg, in fact. So I would also recommend that you convert it into just kilojoule, not even per kg, multiplied by mass. And then when you substitute everything, the delta Q will come out to be minus 318.7 kilojoule. So I'm aware that I got a bit confused in the end there. But what is important is the above process, not the final solving of the question, because anybody can do that. This entire process is more important. In the next tutorial, we'll be solving one or two such more types of problems, but with slight variation. Like the piston can be below the stops and it can go up and something, and things like that. So, yeah.